Welcome to Silverlight Education.
All right, today we're going to go on a pretty fascinating journey, an evolutionary journey, actually. We're going to dive into how one of the body's most critical systems, the circulatory system, had to adapt and basically redesign itself to handle some incredible new challenges over millions and millions of years.
So what we're doing here is breaking down the key ideas from Unit 5 of the BZYCT 133 course, and we're going to focus on the incredible story of, you guessed it, the circulatory system.
So here's our roadmap. First, we'll start with the basics. Think of it as the ultimate delivery service. Then we'll look at the first real model, that simple pump you find in fish. After that, things get really interesting. We'll talk about the game-changing move to land, which, forced a total redesign. And finally, we'll get to the grand finale, the high-performance engine that powers animals like you and me.
Okay, before we trace this whole evolutionary story, we really need to get a handle on its core purpose. What's the circulatory system's fundamental job anyway?
Honestly, the best way to think about it is as the body's ultimate delivery network. It's like the FedEx or Amazon Prime for your cells. Now, if we want to get a bit more technical, it's the organ system that moves blood and lymph all through the body. It's this massive transport network, right? With the heart as the central pump and the arteries and veins acting like the highways and side roads.
And what's it delivering? Well, pretty much everything essential for life. This network is dropping off oxygen and nutrients to every single cell. Then it's picking up the trash, stuff like carbon dioxide and metabolic waste. But that's not all. It's also the Uber for hormones and for deploying your immune cells to fight off infections. It even helps regulate your body temperature. Seriously, without this delivery service, none of us complex organisms could even exist.
Okay, so we've got the what. Now let's get into the how. Let's dive into the evolutionary story, starting with the absolute simplest design we find in our vertebrate ancestors.
The evolution of the heart tells a really clear story. It's all about increasing complexity over time. It started as just a simple pulsating cube in our earliest ancestors. From there, it evolved into the two-chambered heart we see in fish, then a three-chambered version in amphibians, and finally, it landed on the powerful four-chambered heart that birds and mammals, like us, depend on.
So this system in fish, it's called single circulation. And yeah, it's pretty much exactly what it sounds like. Blood passes through the heart only once for each complete trip around the body. The deoxygenated blood gets pumped to the gills where it picks up fresh oxygen, and then, here's the key part, it flows directly to the rest of the body. It doesn't go back to the heart first. And for an animal that lives in water and breathes with gills, this is actually a super efficient design.
But the story takes a really dramatic turn when life decides, hey, let's leave the water. The development of lungs, which you need for breathing air, created a whole new set of engineering problems.
And this was the big one. This was the central challenge. All of a sudden, you have this new destination, the lungs. So the pump now needs to send blood to the body and to the lungs. And ideally, you don't want the oxygen-rich blood coming from the lungs to mix with the oxygen-poor blood coming back from the body. How do you do that? It was a massive, massive engineering problem that evolution had to crack. So what was the first big innovation? Just add a new room, a new chamber. See, the fish heart has one receiving chamber, the atrium, and one pumping chamber, the ventricle. The amphibian heart evolved a second atrium. And just that one simple addition created a whole separate loop just for the lungs. This was, you could say, the birth of the double-circuit system.
Now, this was a brilliant step forward, but it wasn't perfect, not by a long shot, because while you now had two atria receiving blood from the body and lungs separately, they both emptied into a single ventricle. And what does that mean? It means the oxygen-rich and the oxygen-poor blood were destined to mix in that main pumping chamber. And that, of course, really limits the whole system's efficiency. So then reptiles came along and took the next logical step. Their three-chambered heart has this really crucial upgrade, a partial wall called a septum right inside the ventricle. Now, this wall doesn't seal things off completely, but it does a way better job of keeping the two bloodstreams separate. And the result? Less mixing, higher efficiency, and it really paved the way for a more active lifestyle on land.
And that brings us to the final chapter, the high-performance engine. This is where the pump was finally perfected to meet the insane energy demands of a warm-blooded lifestyle.
This is it, the perfected double circulation system. The blood passes through the heart twice for every single cycle. Think of it like two loops. The first loop, the pulmonary circuit, is just a quick trip, heart to lungs and back again, just to grab oxygen. The second loop, the systemic circuit, that's the main event. That's pumping that freshly oxygenated blood out to the entire body. This two-pump system is the absolute key to getting high pressure and maximum oxygen delivery.
And what was the final, revolutionary innovation that made this possible? A four-chambered heart. That partial wall we saw in the reptile heart, it became a complete wall. It sealed off completely, creating two totally separate ventricles. So now, with two atria and two ventricles, the mixing of oxygen-rich and oxygen-poor blood is gone, completely eliminated. And that creates the super-efficient engine you need for a high-energy life.
And if you look at the performance data, the advantage is just crystal clear. You can see a direct line between the number of heart chambers and how much oxygen the blood can carry. And who's at the top of the chart? Birds and mammals with their four-chambered hearts. That is definitely not a coincidence.
I love this analogy. Think of it this way. A high-performance engine needs high-octane fuel, right? Well, for the biological machine that is a warm-blooded animal, that fuel is pure, unmixed, oxygen-rich blood. And the four-chambered heart, that's the engine that makes it all possible.
So let's wrap this up. What's the big takeaway here? The heart's evolution is this incredible story of increasing complexity, and it was all driven by one thing: the rising demand for energy as life moved onto land. The single biggest engineering problem to solve was keeping the oxygenated and deoxygenated blood separate. And the four-chambered heart, it isn't just one more step in the process. It's the ultimate solution. It's the absolute peak of circulatory efficiency.
You know, this whole journey leaves us with a really fascinating question to ponder. After going from a simple little tube to this amazing, incredibly efficient double pump, what could possibly be evolution's next move? What's the next step for the circulatory system? It's definitely something to think about.
And that's where we'll leave it for this one. We will meet you in the next lecture.